This is a demonstration of NanoAD, the Boole logic anomaly detection tool. The NanoAD can be used to detect anomalies in video streams, multi-sensor arrays, and in streaming data. In this demonstration, we'll use the NanoAD to create a new anomaly triggering mode for an oscilloscope and use it to detect anomalies that are invisible to commercially available oscilloscopes. The signal you see is periodic with some noise. The scope is in its free-running mode with no acquisition trigger. We can try to get a better idea of the signal by setting a voltage threshold like this. We can see a bit more of what's going on, but the scope is triggered hundreds of times per second. I've introduced two artificial anomalies into the signal. These anomalies can't be detected by a threshold crossing since they're below the minimum and maximum background signal levels and have similar slopes. The NanoAD uses unsupervised learning to characterize the background signal pattern, regardless how complex it is, and then enters detection mode where it triggers the scope when it detects any significant departure of the signal from the background pattern. No prior knowledge of the anomalies is needed, and there is no limit to the number of anomalies that can be detected. I'll turn off the signal generator, and then switch the scope to its anomaly detection mode and clear the screen. Now I'll restart the signal generator. The scope is learning the background pattern and will soon switch to detection mode. I inserted the anomalies at approximately 20 and 30 seconds into the signal. Now we wait as the NanoAD looks for any deviations from the background pattern. There's the first one. And there's the second one. Finally, I'll turn off the signal generator, and the NanoAD also detects that change as an anomaly. To explain how the NanoAD works, I will show some information about its internal state. The right graph shows a semi-log plot with the time on the horizontal axis and the number of learned clusters on the vertical axis. The steep rise in the number of clusters happened when I turned on the signal generator. The red bar indicates when the NanoAD switched from learning mode to detection mode. The first two yellow bars show when the two anomalies were detected, and the third one shows when I switched off the signal generator. The left graph shows the relative anomaly indices of the various clusters. The horizontal axis shows the cluster IDs, and the vertical axis shows the anomaly index for each cluster. Clusters with anomaly index close to 1 are more anomalous than clusters with index closer to 0. The controls at the bottom define properties of the learning and detection. Two parameters that are most relevant to this demonstration are the percent variation and the anomaly threshold. The percent variation determines how much variation is allowed in clustering subsignals acquired by the scope. A smaller percent variation will produce more clusters as it will have a lower tolerance for variation between subsignals assigned to that cluster. The anomaly threshold determines when the scope will trigger. If a subsignal is acquired that has an anomaly index greater than the current anomaly threshold, then the scope acquisition will be triggered and the sweep will be displayed on the screen. Lowering the threshold will trigger the scope more easily, as I will now demonstrate, beginning with resetting the learning. The oscilloscope is still set to trigger on anomalies, so the NanoAD is acquiring and clustering every incoming subsignal. The input voltage is flatlined and all subsignals are assigned to cluster 1. Now I'll turn on the signal generator and things will start happening very quickly. The first thing we see is a very rapid rise in the cluster count as nearly every subsignal is creating a new cluster. The red bar shows when the NanoAD switched from learning mode to detection mode, and also the graph at the left begins to display the ongoing measurements of anomalies among the 600 or so clusters. In the current mode of operation, the NanoAD continues to learn even as it displays any detected anomalies. On the left plot, active clusters being matched in the current signal are displayed in yellow, and inactive clusters are displayed in gray. The vertical height above each cluster ID shows its anomaly index, with the most anomalous clusters having value close to 1. By lowering the anomaly threshold, we can trigger on more common signals. A low anomaly threshold will trigger the scope more often, and typically it's clear from this plot where one should set the anomaly threshold. Values near 0.9 are very common as useful anomaly thresholds. I now turn off the signal generator, and you can see that it appears that all clusters are inactive. In fact, only the cluster representing the flatline signal is active, and the NanoAD continues to cluster the incoming subsignals, assigning all of them to cluster 1. Turning the signal generator back on, we see that the clusters from before are active again. This shows that the NanoAD can remember clusters by ID, and this learning can be saved and reused.